Einstein's view of gravitation was very different than Newton. Newton was thinking of forces between objects. And he didn't quite imagine how the forces would project from one object to another. That was always a mystery. On the other hand, Einstein replaced that spookiness with probably something that's just as spooky, and that was this notion of gravitational waves.
LIGO stands for Laser Interferometer Gravitational Wave Observatory. The W didn't fit in there, so we just hyphen it. LIGO's goal is to detect gravitational waves. Gravitational waves were predicted by Einstein's theory, but they have never been directly detected. We have very strong indirect evidence, and we all believe his theory, but we never saw these waves directly, so that's what we want to measure them.
Newton's description of gravity was basically that it was a force that was proportional to the masses of bodies and inversely proportional to the square of their separation. Einstein's concept was to look at the body's influence on the space they're embedded in. And so in Einstein's picture, a massive body makes a depression in the space-time around it, so that other bodies following their natural paths tend to be attracted to this depression. The two ideas sort of come up with the same answer when we're describing, say, the orbit of the Earth around the Sun, or the Moon around the Earth, or the falling of an apple. But they differ if you think about what is the effect of a very rapid change. For example, if two stars collide or a star explodes, somehow the change in the mass distribution, the presence or absence of a star where there was one before, has to somehow be communicated throughout the whole universe. And in Newton's picture, there's a problem with that, because there isn't any way for that information to take some finite amount of time. Somehow the whole universe must know about everything instantaneously. It's called the problem of action at a distance. So going back to Einstein's picture, if you think of it in terms of massive bodies affecting the space-time, you can immediately think of a way to communicate information about those bodies from place to place through ripples in space-time.
The waves can be represented by this object I found on a wine bottle, and it's a mesh that you can see. And the waves cause transverse to the direction in which they're moving. They're moving forward. And transverse to that, the space gets tugged like this and collapses like that, tugged like this. And if you look carefully at this, and I'll do this a few times, you'll notice that the little squares in this are exercising a motion where along one direction, it's obvious which direction, I mean the direction I'm pulling in, space is getting expanded, but transverse to that, up and down, space is getting contracted. And that's the key to the whole thing.
LIGO is laid out in an L shape. And each side of the L is 4 kilometers long. 4 kilometers was chosen because the American taxpayers are willing to pay for it, and it's far enough to get an effect that we think we can see. The reason it's an L shape is because gravitational waves cause objects to get closer in one axis and farther in a perpendicular axis, and then vice versa. So we fill the two arms with light from a laser in the corner station, and the light spends about 1/100th of a second in this arm and 1/100th of a second in the other arm, and then the light comes back to the corner station, and the light that spent time in this arm comes back a little bit before or a little bit after the light that spent time in the other arm. And that's how we would detect the effect.
A lot of people try to think about how to produce gravitational waves so you could measure them, and then you have an experiment like you do with radio. You produce the waves, you detect them, and then you prove that they exist. But with gravitational waves, it turns out that you need a lot of mass and very high accelerations in order to make any distance change at all by even a minuscule amount that you can measure. So everything produces gravitational waves, but it's only big things out there. It's big black holes, big neutron stars that are accelerating and colliding and exploding, and it's that kind of events that produce gravitational waves of such magnitude that we can measure them.
The prediction is that gravitational waves are always occurring. The reason why we don't notice them is that they're exceedingly weak. They're very hard to imagine how weak they are, but for our detector, for LIGO, we're looking for displacements of the test masses at the two ends that will be something like 1,000th the diameter of a proton over a scale of 2.5 miles on a side. So we're looking for substantially smaller displacements than the kind of things that people normally experience and measure.
When we begin detecting gravitational waves, it's going to be in the newspaper everywhere because it's going to be the first time we see gravitational waves. But once we begin seeing them routinely and we can classify them, these come from black holes, these come from neutron stars, these come from supernovas, then we can learn a lot about these sources.
I think one of the really big motivations for looking for gravitational waves, in addition to all the wonderful forms of energy that we observe our universe in, is precisely this fact that they're entirely responsive to the distribution of matter. And so if we can detect them, we'll see what's going on in the cores of the objects, the most dense and the most active parts. And even though it's quite challenging and it hasn't been done before, the promise is that we'll reveal effectively a different universe than we've seen before.
And that's what makes it so exciting for most of the people in this business. It isn't just one number you're looking for, or this experiment isn't over when one makes one discovery. It has a lovely, distant, wonderful future with many, many new things that will come.